We're now up to day 7 for Chapter 1 for Physics 12, and this is the first of 2 lessons that deal with ramps, sometimes called inclined planes. You know, we have like a driveway that's heading downhill and you're watching some car pick up speed. We did this in Physics 11 a little bit. In fact, let's start with that. So we're up to section G in our notes here now. And let's just review what we did see in Physics 11. We looked at this very briefly, and we said, well, we'll only look at stories that do not have any friction. And we'll take a quick look at a way to find the acceleration of something going down a hill, but we won't talk about why it's true. And so here's just a little review picture of what we said in Physics 11. For any given hill, you might find some spot, you know, up here where you can do a couple of measurements. You would measure the height of the hill and then the diagonal length of the hill that object's going to follow. And if you knew the height and the diagonal length to one point, like that little pink point that I've got there, then you can actually find the acceleration on the hill. And the acceleration is actually 9.8. It's g, 9.8, but multiplied by the sine of the angle of the hill. And one easy way to find the sine of the angle of the hill, if you think about just opposites and hypotenuse, is to just do h divided by d. And we actually more often did h divided by d than we actually use the sine of the angle. So today we're going to take a look at not only why is that true, but we're even going to upgrade it and install some friction options in there as well. So that was, option 1. Just trust the Physics 11 idea, but it only works if there's no friction at all. Let's do a more elegant approach here. We'll call this part 2. Let's do this with friction, very Physics 12-ish. And at the beginning, we're going to take a look at what happens if the object is sliding down the hill. If you give an object a kick, then you could actually watch it slide up the hill to a stop, and we'll do that one in a minute. But let's start off by the more common one, the more frequently seen one of an object sliding down the hill and perhaps picking up some speed. I would draw this picture actually quite wide because we're going to add a lot of forces to it and we're going to break them all up. So you just need some space. So I've got my hill. Engineers love to talk about the angle down here at the foot of the hill to talk about how steep it is. And I've got some, mass m. I don't know what mass is right now. We'll just call it m. Okay. To get started, the first thing we're going to do is kind of establish our coordinate system. And on any other day, you would do this, but don't follow me today because it's going to be wrong. You would say, well, this could be my x-axis and this could be my y-axis, just like good old grade 9 math. But this object goes this way. It doesn't kind of follow the x or the y-axis. So those choices for your x and y are actually pretty poor. Instead, what works really well is to tip your axis. It's like you take your whole head and you twist it counterclockwise, so that your ears kind of line up like this, okay, in that direction there. And we're going to call that the x direction, and then the y direction will be out of the hill, like that. Since this object is going to go down the hill, it is sliding down, and it's probably picking up speed. That's the usual case. I want to call this x direction to your kind of lower left as being positive. And just to be really overt about that, allow me to add a little hand in here and say that away shall be called positive when we go to do F net equals ma. Okay, here goes. Let's start adding some forces to this picture. Got good old force of gravity. And on any other day, you would go, yeah, that looks pretty good. That looks fine. But today, if you've tipped your head, that force doesn't line up with your body anymore. It kind of hits you in your left hip. So what you have to do is take that force and break it up into 2 parts. One of which is going to crush into the hill, and the other one is going to slide along the hill. Now it turns out there's a beautiful similar triangle thing going on here, and the civil engineering angle at the foot of the hill ends up being exactly the same size as this angle up here in that little resolution triangle. It will be that way every single time, right? So you can rely on that. This triangle does not have the angle compared to the horizon like we've seen in a lot of other examples, so you do have to think about your SOHCAHTOA. You've got your hypotenuse, and now this is the adjacent, this is the opposite, and when you play around with the SOHCAHTOA, you'll find that the one attached to the angle here can be found by going with the mg weight value, but then multiplied by the cosine of theta. And this one down here is actually mg times the sine of theta. Oops, I kind of broke that there. There we go. An easy way to remember this, I like to think C for cosine, C for crush, as the gravity crushes it into the hill. S for sine, S for slide. That's the part of gravity that tries to slide you along the hill. Okay, wow, all that just for gravity. The next force is the force from the surface, and we call it the normal force. The word normal means perpendicular, like meeting at 90 degrees. So the normal force has to come at 90 degrees out of the hill, right? So, here's your hill, and it has to be at 90 degrees to it. It does not point straight up into the sky. Okay, that would be incorrect. And the other thing is it's not equal to mg. It doesn't have to be. It only has to actually cancel, if you wish, with this force here. So those two are going to be exactly the same size. And that means that the normal force will be tinier than what you've seen before. It's not mg. It's actually mg cos theta. Okay, a little tinier than mg. All right, great. So far, so good. Now that you've got some squish, we can put some friction in. It is sliding, so the equation mu times Fn should be fine. And the Fn is not as simple as mg. Okay, this Fn is actually mg cos theta. So the whole friction term is mu mg cos theta. It's a little technical, but that's how much friction there's going to be. Now remember, we've called this the x direction, right? Kind of in that diagonal up, down, left, right deal. This mg sine theta is positive because it's going down the hill. And this friction force is negative because it's not going down the hill. So now we're going to go, I'm just going to get my F net equals ma ready to go. And we're going to put those two forces, the mg sine theta, the slippery part of gravity, and the friction, the mu mg cos theta. We're going to put that in for F net because that's what we see from the picture. So yeah, getting ready to go. I'm just kind of scrolling that up a bit. My net force would be the portion of gravity, the slippery part, minus the friction force. And so I'm going to have mg sine theta minus mu mg cos theta. Great. Now my plan is to use this to try to figure out what the acceleration is. So I'm going to solve for a. I'm going to trade sides here, spin this around a little bit, and then I'm going to divide by the m. There's an m in every single term. People would say it's mass independent. And so here's a, almost worthy of being on your formula sheet formula. It tells you how much acceleration you've got for this object as it slides down the hill. Now I've kind of loosely said that the direction is down the hill, right? Because that's the direction we called positive. But be aware of this. Although most of the time, the slippery part of gravity will create a larger number here than that force of friction going back. And objects will, for most physics stories, tend to speed up. It is entirely possible, based on angle choices and coefficients of friction that are bigger, to have that number be larger than this one. And so you'll get a negative answer. And so your negative answer is saying, hey, it's this negative number down the hill, or in other words, it's actually back up the hill. So in that case, if the net force is up the hill, this object, although it's sliding down, will actually gradually come to a stop. Okay, it's totally possible for that to happen. So this is the story for the object as it slides down the hill. I'm just going to leave a little note in here. I know technically I've called these forces, and they're not forces anymore because the m's have been canceled out, but I'm still going to refer to them that way. And what you can see is that the gravity and friction forces are battling each other. We've got one positive and one negative. And so they're in a bit of a battle. Gravity's trying to make the object go faster, and friction's trying to make it go slower. Now, we really should spend a whole bunch of time and take a look at what happens if you take a box and put it on a hill and give it a kick. And then after you kick it, watch it slide up to a stop. So let's ponder that for a minute. What about sliding up the hill? Now, if we wanted to be super thorough, we would say, oh, let's draw the whole thing over again. Okay, so here's notes you already have. You're already drawn this. This was the sliding down the hill. And you'd redraw the whole thing for a box that has been kicked and is now sliding to a stop up the hill. But not much changes. There's still gravity. There's still an Fn. There's still going to be friction, but it will be the other way. So here's the only change that you would make for an object that is actually sliding up the hill to a stop. You would actually take that friction force and say, hey, let's put it this way. And now what I can see is this force of friction is lined up in the same direction as gravity. Both of them are down the hill. We're calling that positive. Both of them are cooperating to try to bring this object to a stop. So let's make life simple. Let's just put some notes in here instead of redrawing the whole thing. If you're sliding up the hill, the friction force changes direction. And so now the friction force points down the hill in the direction that we've called positive. And so when you go through all that F net equals ma again, you end up with this. G sine theta plus mu g cos theta. That will definitely be a positive value because you're adding two positive things together. And it will tell you about the acceleration value down the hill that you have to try to bring this thing to a stop while it slides up the hill. So the velocity is up the hill, but the acceleration will be down the hill, bringing it to a stop. Probably worth another little note in there again. I know I'm calling these forces pretty loosely. The masses have been canceled, so they're not really forces. But it's worth the note that these terms, which have come from forces, are cooperating. Okay, the gravity and the friction aggressively try to stop it. So if you take a box, put it on a hill, and give it a bit of a kick upwards, you'll actually see the box go whoom and stop really fast because gravity and friction are both trying to stop it. Then, if there's enough, gravity force to get it going down the hill, it'll go and slowly pick up speed. It doesn't pick up speed with the same aggressive value of acceleration that it stopped at, because on the way down, you actually see this battle, this disagreement over how big the acceleration would be. But here you have some cooperation to get some really big acceleration. Going to do just a couple of examples here. We're going to compare and contrast them. Here's the first. Copy that out there. It says a block of wood slides down with some stickiness there, 0.15. That would be a kinetic coefficient of friction. Down a 4.8 meter long ramp. That's inclined at 38 degrees. The block of wood has an initial speed of 1.3 meters per second. We're going to find the speed of the bottom, 4.8 meters later. Okay, so yeah, sure, we'll pretend this question is actually important, but we're going to talk about things that are more important than just this question. When is it safe to just go and grab a formula from your formula sheet, right? Because, back here, we have these formulas that you could add to your formula sheet, and is it okay to use them? Well, these formulas are fine as long as there is just one box on a hill sliding along, perhaps with some friction. If there's no friction, the mu's would be 0, and suddenly it looks like physics 11. You just have like a equals g sine theta. But yeah, these are perfectly fair things to use when there's just a box on a hill, maybe even having some friction. And as I look at this question, sounds perfect. It's a box on a hill with some friction. So it's okay, and that's kind of the point of this example. It's okay to just grab this equation and say, I know this equation works for things that are sliding down hills. If it's uphill, you put a plus, but if it's downhill, this should work fine. And it does. You can go ahead and just trust the work that you've already done, laying out that free body diagram in your notes. And we can just throw the numbers in and see that the acceleration is 4.8. Now we can go ahead and do our kinematics. This part's really boring, right? This is just the grade 11 kinematic stuff. No, the VI is 1.3. We're looking for VF. Got the displacement. Got the A. Everything down the hill is positive, right? Down the hill, down the hill, down the hill. Don't care about the time. This is the best equation to use there. Done. Super fast. I'm not really worried about the stuff under that pink line there, right? That's the easy stuff. The interesting stuff's above it. And it is okay to simply use this equation because this was a story simply about a box on a hill. So things are fine. Well, I've got one more kind of contrasting example to go with this one just before this lesson is all done. And you're going to first look at it and go, contrasting, doesn't look all that different. So here's the first example, right? Block of wood, slides with a 0.15 coefficient, 4.8 meter ramp, 38 degrees, great. Here's the next one. Block of wood, you probably don't want to copy this because something seems wrong. Block of wood, slides, 0.15, 4.8. That's the same question, right? But wait a minute, let me change it. It's a 4 kilogram block of wood, right? And now right now, thinking critically, looking back at the previous question, you should be going, we really didn't care what the mass was because we could actually, back in the theory, we canceled the m's. So why even worry about it, right? Like, why are you telling me that it's a 4 kilogram block of wood? Well, it is important because there's one more bit of information. Hey, forgot to mention this. Oh yeah, there's an elf pushing the box down the hill with an applied force of 15 newtons. Okay, now it's getting complicated. Let's bundle this together a little bit. Let's just write it like this. So here's what you can copy. Let's say an elf pushes the same 4 kilogram box down the hill with an applied force of 15 newtons. Okay, so new information. There is an elf shoving on it with 15 newtons with their hands, and it's a 4 kilogram box. The The equation from the formula sheet, it's no good anymore. It doesn't have ELFs, right? There's no ELF term in there at all. So you got to start over. We're going to have to do that free body diagram again, but then we can bring the ELF into the story. We'll just put all the forces in, and then we'll look at it, decide the F net, and go from there. So here goes. I've got, for this picture, an applied force from the ELF, shoving that thing down the hill. Now, I know the ELF's up here, and they're going to kind of shove it like that, but we don't show shoves, we always show pulls. So we're going to show that applied force like that. Next thing, I got this weight for this 4 kilogram box. It's almost 40 newtons, right? 39.2 or something. Well, that's no good when you tip your head sideways so your ears line up with the hill. That purple 15 is great, but the mg's not. So we're going to break it up into a crush and a slide. Right? It's always cosine for the crush, sine for the slide. The normal force is as big as the crushing force. It's not as big as mg. Close though. It's as big as mg cos theta. Okay, great. And then one more force. If it's sliding down the hill, there'll be some friction going back. That friction, if it's sliding, will be mu times the Fn. And today it's kind of an exotic version of the Fn. It's mu times mg cos theta. Awesome. So now we can go and start thinking about the net force. We've got this force here, and this force here. Those are all acting in the direction of motion. So we need to think about what they're going to add up to. Right? The 15 is forward, the mg sine theta is forward, the mu mg cos theta is backwards. We'll just tell F net equals ma about that. So yeah, we've got a forward 15, got a forward mg sine theta, and a backwards mu mg cos theta. And it's going to make that mass accelerate. There is no mass on the 15 term, so this is not a mass-independent problem. You'll have to keep that mass, that 4 kilograms, in all of those other terms, and then plug and play from there. Okay, so there goes in the 4. Done. Now, I'm not even going to bother like finishing the second part of this question, which said, oh, well, you got to go and do vf squared minus vi squared equals 280. Yeah, whatever. That's not why we're doing this example. The idea of doing this example is be careful. You know, if there's something added, like an ELF or some other rope or something, then you can't just use that equation that we threw a box around a minute ago. You have to go back and do F net equals ma, and then it works great. And so that's our first day at looking at ramps. Some key things there. The mg needs to be broken down into 2 perpendicular forces, a crush and a slide. The normal force is as big as the crush. It's as big as mg cos theta. And you got to use that mg cos theta when you go to calculate the force of friction. It's mu times mg cos theta. Then it's just our usual game of F net equals ma.